Okay, so welcome back to the afternoon session, the third keynote talk of the ACM India Annual Event 2021. It's a pleasure to introduce Professor Kurt Melhorn, who is the speaker of this session. He's well known for his work in data structures and algorithms. He was the director of Max Planck Institute for Informatics for over 20 years, and he's currently a director emeritus. As we were discussing during the break, he has strong connections to India, as not only he is well known to theory community in India, he also knows, and is because he has mentored most of the theory people in the country, because almost quite a few of them have done their either postdoc or visited Max Planck Institute during their career. And if you visited MPI, it's very hard not to run into Kurt. Kurt is also the person behind the establishment of Indo-German Max Planck Center for Computer Science, called IMPEX, between Department of Science and Technology India and Max Planck Society at IIT Delhi about a decade ago, which further strengthened the interaction between these theory group in India and the Max Planck Institute. Kurt's research interests span a wide variety of areas, including data structures, computational geometry, computer algebra, parallel computing, VLSI design, computational complexity, combinatorial optimization, and graph algorithms, where he has published nearly 300 articles. He had written 3 volumes of popular textbook on data structures and algorithm, which was a popular undergrad textbook. He's also been an important figure in the development of algorithm engineering, implementation and experimentation of algorithms, and is one of the developers of LIDA, the Library of Efficient Data Types and Algorithms. As I said, Kurt has played an important role in the establishment of several research centers for computer science in Germany and all over the world by mentoring a number of PhD students and postdocs. He also initiated the Research Center for Computer Science at Dachstuhl, which I know many computer scientists would have benefited by attending these conferences. And he started this European Symposium on Algorithms. Kurt has received several prizes for his work, including Leibniz Award, EATCS Award, Zeus Medal, ACM Paris Kanellakis Theory and Practice Award, Erasmus Medal of the Academia Europaea, to name some. He holds honorary doctorate degrees from Magdeburg, Waterloo, Aarhus, Gothenburg, and Patras universities, and is also an ACM fellow. And today he is going to talk about fair division of goods. And I believe even that has an Indian connection because there's some collaboration with some Indian researchers. So over to you, Kurt.
Thank you very much. Thank you very much for this kind introduction. It's a pleasure to be here. I have, as Venkatesh said, I have very good connections to India. I have very good friends in India, colleagues in India. I spent twice my winter vacation in India. It's a beautiful country to travel. I make sure that almost every time I go to India, I visit Agra. I've visited Agra now 5 times, and it's just, I think it's the most beautiful place in the world. So let me start with my talk. Let me share my screen. Here it is. View full screen. So you should all be able to see my screen?
Yes.
Yes, okay. So I talk about fair allocation of indivisible goods. This is joint work with Bhaskar, who is here on the left. Then Jugal, who is here on the right. Then Kavitha, who is here, and Alkmini. Okay, so what is it about? So I first should thank Bhaskar for allowing me to build on his slides. All the beauty in the slides is his. So we are given a set of agents. We are given a set M of indivisible goods, and I use little m for the number of indivisible goods. So think of things like a house, a car, a toothbrush, so things which cannot be divided. I mean, otherwise they lose value, you destroy them. And every agent has a valuation function, so he assigns a value to every subset of the goods. So if S is a set of goods, Vi of S is the value of this bundle of goods to agent I. And the only thing we're going to assume about this function is that it is normalized. So the empty set has no value and that it is monotone. Getting more never hurts. So this is this here. And in the second part of the talk, I will restrict this to additive valuations. An evaluation is additive if the value of a bundle of goods is simply the sum of the values of the goods in the bundle. And our goal is to partition the goods into bundles, one for each agent. So Xi is the bundle assigned to agent I, such that this partition is fair. And I will discuss fairness in a moment, what are notions of fairness. By the way, you can interrupt me at any time. If you have a question, just interrupt me. I don't know how we do this technically, in the chat or somehow, or you can turn on your microphone and you just interrupt me. The problem also makes sense for divisible goods, of course, and then it's a simple problem, isn't it? Well, if you think of divisible goods like water or salt or money, mathematically money is not really divisible, but in a practical sense, money is divisible. Then these are homogeneous goods, and then it's simply, I mean, if you have a kilo of salt and you need to divide it through 3 people, you give 1/3 to each. It's more difficult if you want to divide a cake, because let's say you have 3 people and there is a cake with 4 candles and there are nuts in it, and there are and the people value the candles differently, they value the nuts differently. Some people like more of the chocolate, some like less of the chocolate. And then it becomes a non-trivial problem, even for divisible goods. And let me first tell you what is known about divisible goods. So for divisible goods, the problem was introduced by Steinhaus in the 40s. And there the goal is, what is the cake? Mathematically, the cake is just the unit interval. And what is the valuation function? So for each agent I, it has a valuation function for the unit interval, and the area under the curve is 1. Yeah, so this guy gives particular value to the first part of the cake, and he also likes the last part of the cake, but he doesn't like the middle part of the cake. Yeah, and each agent submits one of these valuation functions. And the goal is then to divide, to partition the cake such that there is no envy. What does it mean there is no envy? If you look at the ICE agent and the value he gives to his bundle, this should be at least the value he assigns to any of the other bundles. Yeah, so every agent thinks that his bundle is the most valuable, or that none of the other bundles is more valuable. For n equal to 2, there is a simple solution, a solution which you all know, cut and choose. So here is the cake. The first agent divides it in 2 parts, such that for him, both parts have the same value. And then the second agent chooses. Yeah. So this is what the first agent does. He cuts the cake into 2 parts of equal value, and then the second agent chooses. For n larger than 2, the problem is quite complex. So for n equal to 3, 2 people independently found solutions, Selfridge and Conway, John Conway in the 60s. Then for arbitrary n, a solution is only known since 95 by Brahms and Taylor. For the solution by Brahms and Taylor, the number of cuts, the number of pieces in which the cake was divided. So, I mean, the unit interval is divided into pieces, and then each agent gets a subset of these pieces. The number of pieces was not a function of n, was not bounded by a function of n, and only since 5 years it is known how to cut such that the number of parts is bounded by a function of n. Yeah, so but it's a huge function of n, a humongous function of n. So there is still, even for the divisible case, the case for the dividing a cake, there's still work to be done. Okay, what are applications of discrete division? Well, the obvious one is divorce settlements. Then you need to divide into 2. Inheritance property, then you need to divide among the children. Here in the left lower corner, you see an advertisement by one of our local lawyers. I found that on a billboard here in the city. And it says, "Does your brother enjoy the heritage in the son? Yeah, and do you feel treated unfairly? Then come to us." Yeah, so dividing goods, divorce settlements, set it a heritage, splitting rent. Yeah, you have people share an apartment, the rooms have different quality. How do you split the rent? How do you divide chores at home and the household, papers to review? How to allocate students to courses? So there are many applications of discrete division. And there are even 2 websites. One is called Split It, and the other one is called Fair Outcome, where you can go and they compute solutions for you. Yeah, for example, how to split rent, or how to split the cost of a taxi ride. Okay, so so we had already this notion of Envy-Freeness. Let's now recall this. So we say an allocation. Recall that X is this partition of the set of goods into n parts, 1 part, 1 bundle for each agent. And we say that this allocation is envy-free if for any 2 agents there is no envy, meaning the ICE agent finds that his bundle is at least worth as much as any other bundle. Is there always a fair envy-free allocation? No. Consider the simple case. We have 2 agents, a single good, and both have positive valuation for this good. You have to give the good to one of the agents, and then the other one will envy. Yeah, so envy-free allocation does not exist in general. So what about relaxations? The first relaxation that was studied was introduced by Budish in about 10 years ago. It's called envy-free up to some good, up to 1 good, called EF1. So an allocation is EF1 if the following holds. After removal of some good in the J's bundle, I does not envy anymore. Yeah, so in particular, if you choose as G the most valuable good, for I in Xj, and you remove it from the bundle, from the J's bundle, then I should not envy anymore. Let's see an example here. Let's say we have 3 goods, a house, a car, and a toothbrush, 2 agents, and the valuation is sort of the obvious one. A house is much more valuable than a car, and a car is much more valuable than a toothbrush. Then if you give the car to the second agent, and if you give the house and the toothbrush to the first agent, then this is EF1. Why is it EF1? Well, first, the first agent, secondly, definitely doesn't even envy the second one. The second agent, yeah, agent A2 envies agent A1, but if you remove the house from the bundle of the first agent, the envy goes away. So this is an EF1 allocation. Okay. So we can again ask, do such EF1 allocations always exist? And the answer is yes. This was shown by Lipton and others about 15 years ago. So it was shown even before the name was coined. But clearly the example on the previous slide shows that this is not a very satisfactory notion of fairness. Yeah, we have this, one guy gets the toothbrush and the car, and the other one gets toothbrush and the house, the other one gets the car. And you must say, well, yeah, it's true, I envy you, I really envy you. I mean, I only got a car, you got a house and a toothbrush, but it's not so bad. I mean, after one takes the house away from you, I'm fine. It's not very satisfactory. So therefore, there is a more stringent notion called EFX, envy-freeness up to any good. And the condition is now not for some G in Xj, but for all G in Xj. So in particular, for the G in Xj that is least valuable. To I. So our allocation from before, where we give the house and the toothbrush to one of the agents and the car to the other one, this is not EFX. Why is it not EFX? Because, yes, the second agent envies the first, but after removal of the toothbrush, the envy doesn't go away, yeah, because the house is still worth more than the car. So this is not an EFX allocation, but there is also an EFX allocation. Namely, you give the house to the first agent and the car and the toothbrush to the second. Then the second agent, there is no, I mean, the envy goes away after removing the house, and the first agent doesn't even envy the second. So this is an EFX allocation. Yeah, are you all with me? So we have now seen EF1, where the envy goes away after the removal of some good. And I have defined EFX, where the envy goes away after the removal of any good. And yeah, we can again ask, does this always exist? So let me introduce one more notion, strong envy. So I say an agent strongly envies a set of goods if it envies a proper subset of it. And then we can also say an allocation of is EFX is no agent strongly envies some other agent. No agent strongly envies the bundle of another agent. And we can ask, is there always an EFX allocation? And this is open. We don't know whether it always exists. There's also no counterexample. And sort of, yeah, I don't really know what I should believe. We have worked on trying to prove that it exists. We have worked on trying to disprove that it exists. And yeah, let me tell you what we know. So this should be, for two agents, it always exists. And two agents and additive valuations. And this is a refinement of cut and choose. Let me explain it to you. So the first agent cuts, and then the second agent chooses. So the first agent does what? he creates two empty bundles. And then he looks at the goods one by one. But he looks at them in a particular order. He looks at them in decreasing order of value to him. Yeah, in decreasing order of value to the first agent. And what it does, it always assigns G to the bundle of smaller value. So maybe I should not draw it like this. I should draw it like this. And he adds the first good here. Then the second good, which is smaller, he adds here. So this is the good one. The second good he adds here. The third good he adds here. Then the fourth good goes again over to the other side. Here in my example, the fifth good would also go to this side. Then the next good is always going here. And so the two bundles, they overtake each other from time to time. But the advantage of the more valuable bundle is never more than the least valuable good in this bundle, right? Because when does a bundle overtake another bundle? It was lower before, and then you add one. And so the advantage now is at most the value of the good that you just added. But since you add goods in order of value, in decreasing order of value, the advantage is never more than the value of the last good that you added. And this is the least valuable good in the bundle. And therefore, the two bundles, no matter which of the two bundles you give to agent one, it will not strongly envy the other bundle. Because if you remove the least valuable good from it, the last one added, it becomes less valuable. Yeah, so there is no, so agent one is fine with either bundle, and agent two just picks his preferred bundle. So that means for n equal to 2 and additive valuations, it always exists. And it's a refinement of cut and choose. Now, what is known in general?
Good. There is a question.
Yes.
Neil, do you want to ask?
Okay, thanks. So I was just wondering, even in the EFX example that you shared with the house and the car and the toothbrush, it still takes the removal of a house to eliminate envy. So I was wondering if there is a notion of envy-freeness that takes into account the difference in the magnitude of the valuations of the two bundles.
Yes, there is also, okay, there is a notion that you get your minimax share. So you can also think of the problem as follows. You say, I choose a partition, and then I get the least valuable bundle in the partition. Yeah, so this is sort of also a generalization of cut and choose. Yeah, because agent one divides, and then he gets one of the two parts, and he might get the one which is less valuable to him. Therefore, it's the good thing to do is to divide it into even parts if you can. So you can ask this. So you can say every agent, there is a certain value which he could guarantee for him if he chooses the partition and then gets the least valuable good. And then you can ask whether there is a partition which guarantees this value for everybody. And the answer is no.
Okay.
It was shown that there is an example of 7 goods and 3 agents where it does not exist. But you can guarantee something like, I don't know the exact number, I think 3/4, you can guarantee for everybody. So there's that takes the value of the goods into account.
I see. So something can be achieved approximately, but
Yes.
but not if you demand it entirely. All right, that's very helpful. Thank you so much.
You're welcome. So this is what is known. For n equal to 2, I've just shown you it exists for additive valuations, but it exists in general, also for general valuations. This was shown by Plaut and Ralph Garden in 1918. For any n and identical evaluations, it exists. For n equal to 3 and additive valuations, it exists. This was shown by Bhaskar and Jugal and myself and appeared in EC this year. It got the award for an exceptional paper award. For n greater or equal to 3, it's open. For n greater 2 and general valuations, it's open. And for n greater or equal to 2, general valuations and charity, it exists. And one of the papers is by us and appeared in SODAV this year. What is this? What is this charity? So there we partition the goods into n+1 bundles. And the n+1 bundle goes to charity. The other n bundles are given to the agents. So xi, the ice bundle, is given to the ice agent. And this allocation of the goods without the goods that go to charity is EFX. Also, the number of goods that go to charity is not too big. And the value of the goods that go to charity is less than the value of any of the bundles. Yeah, so none of the agents says we are absolutely crazy. We give, everybody says, what I got is at least what we have given to charity. And what I plan to do in the following, I want to show you this result. I want to show you how we do this. And then in the last 5-10 minutes, I will talk about this. I will only briefly talk about this because it's very technical. The paper is a 20-page case distinction, so it's not the most elegant paper, I would say, but I think it's a very nice result. So I encourage you to read it. Okay, so there's a very important notion which is called the envy graph. So we have an allocation X. And we draw an edge from I to J if the ice agent envies the J's. Yeah, so if the value of bundle Xi for agent I is less than the value of bundle Xj for agent I. So here is an example. The blue edges denote envy. And the first thing I want to show you is that we can always assume that this envy graph, or we can always achieve that the envy graph is acyclic. Namely, assume there is a cycle, like here, A3, A4, A6, A5. Then what you can do is you can reassign the bundles of the agents in the cycle by doing the following. You just take the bundle X5 and you assign it to agent A6. You take the bundle X6 and you assign it to the agent A4. You take the bundle X4, you assign it to the agent A3, and you take the bundle X3 and you assign it to the agent A5. So more generally, if you have a cycle, you take the bundle of the ice agent in the cycle and you assign it to the one which is before in the cycle, so the one which envies. In this way, all agents on the cycle improve. And for the other agent, nothing changes. They keep their own bundle, so they might still envy goods as before. But all the agents on the cycle improve, and so we can continue this until the envy graph is acyclic. And this will happen at some points because agents cannot improve forever. Yeah, so we can decycle the envy graph, and the important thing is when we decycle, none of the agents is worse off after decycling. Yeah, and agents might keep their bundle or agents improve, and this monotonicity will be very important in what follows. monotonicity. Okay. So I can next show you that EF1 always exists. Yeah. Remember what is EF1? If I look at the ice agent, it does not envy the J's bundle after the removal of a G for some G in Xj. And here's the algorithm. It's a very simple algorithm. You initialize all bundles to the empty set, and all goods are unallocated. Then you look at the goods one by one, and you keep an invariant of this loop now, namely that the current allocation is EF1. This is certainly true at the beginning if all bundles are empty, and that the envy graph is acyclic. This is also true at the beginning because there is no envy at all. So if the envy graph is acyclic, then you have a source in the envy graph. Yeah. So this is a source. And you assign G to it. Yeah. So you have XS and you add G to it. And then you decycle. So let's see. Why is it still EF1 after adding G to a source? Well, because S is a source, nobody envied XS. And so we can safely add the G to it, because if we fictitiously remove the G again, nobody will envy it. It will envy the source. So the allocation is still EF1. We might have introduced cycles. So we decycle the envy graph, and then we can add the next good. So EF1 is easy to achieve and was done by Lipton and others in about 15 years ago. Okay, now let's do EFX. So the algorithm is again not too complicated. So again, we start with all bundles empty. We have all goods unallocated. And I explicitly introduce a set P now for pool. This is the pool of unallocated goods. Then we have 3 update rules, U1, U2, U3, and I will go through them in a moment. We maintain the invariant that the envy graph is acyclic and that our current allocation is EFX. Then we apply the update rule. This will change the allocation and the pool. And we will make progress in the sense that no agent is worse off by this update, and at least one is better off. Yeah, so for at least one agent, the bundle improves, and for no agent, the value of his bundle goes down. And again, the update rule might introduce cycles into the envy graph. We decycle. And the update rules change the allocation and the pool of unallocated goods. And the pool of unallocated goods, it's not true that it's monotone, that it goes down, that we might add a good which was already assigned to an agent back to the pool. Yeah, so this pool shrinks and grows in size, but termination follows from monotonicity, because the update rule makes sure that no agent is worse off and at least one is better off. And decycling also has this property that no agent is worse off and at least one is better off. And since the the value of the bundle of an agent cannot increase indefinitely because there are only 2 to the m choices, it must stop at some point. Okay, now what are these update rules? the update rule U1. This update rule is applicable whenever there is an agent that envies the pool. Yeah, so we have the pool of unallocated items, and there is some agent which envies the pool. And now we ask ourselves, to whom should we give the pool? Should we give the entire pool or a subset of it? Which subset? And recall this definition of strong envy. I say an agent strongly envies a set of goods if it envies a proper subset. If there is some agent which strongly envies a set S of goods, you should not give this set S to an agent, to another agent, because then you will have envy even after the removal of a good. So this leads to the notion of a minimal envied subset. So we start with the pool. And we assume that the pool is envied by some agent. So Z is now envied by some agent. And as long as some agent envies a proper subset of Z, yeah, so strongly envies Z, we take a good in Z such that Z minus G is envied by some agent, and we remove G from Z. So we have the invariant that Z is envied by some agent. Now, when we leave the rule, the loop, Z is still envied by some agent, but it is not strongly envied by any agent. Yeah? When we go out of the procedure, when we leave the while loop, Z is still envied by some agent. We made sure that we always remove the good such that after we remove, there is still envy towards the set, but we remove as long as there is strong envy towards the set. So the algorithm determines a minimal with respect to set inclusion, subset of subset Z, that is envied by some agent. Yeah, Z is envied by some agent, but not strongly envied by an agent. And now here comes the update rule, the first one. So we assume that X is E of X and some agent envies P. We determined a minimal envied subset of the pool as described on the previous slide. We assign this Z to an agent that envies it. We choose an agent that envies Z, and we assign Z to I, and we change the pool to, well, we remove the Z from the pool and we add Xi to the pool. And now clearly I is better off. And because it did not strongly envy any other agent before, it still doesn't strongly envy any other agent. And I is not strongly envied by any other agent because Z is a minimal envied subset. Yeah, we made sure that we choose a Z that is not strongly envied by anybody. So this is our update rule 1. Then comes the update rule 2 that is trivial. It is applicable whenever there is a good in the pool that you can just give to somebody without introducing strong envy. Then you remove G from the pool and you give it to I. And clearly agent I is better off than before. And now comes the third rule, which is the most complicated. So the third rule is applicable whenever U2 is not applicable. So you cannot add just a good to an agent. And there are still, the number of goods in the pool is still the number, at least the number of agents. So let me do a warm-up first. Assume the envy graph has a single source. So here is the source of the envy graph. And you can reach all the agents from this source in the envy graph. Then you take a good from the pool and you add it tentatively to the bundle of the source. Now this will in general introduce strong envy. So we take a Z, which is a minimally envied subset of XS union G, and we take an agent I that envies it, that envies the Z. Now, since everybody is reachable, since the envy graph has a single source, there is also an envy path from S to I. So now we have a cycle in the envy graph, and we just take this cycle and improve everybody on the cycle, as we did it before. And yeah, what do we do with the pool? We remove the G from the pool, and we add everything in XS union G minus Z to the pool. Yeah, so this is, if there is, the envy graph has only one source, we do this. We tentatively add G to the bundle of the source. We determine a minimally envied subset, Z. We find the agent that envies the Z. Then we have a cycle in the envy graph, and we decycle. And this now, in general, the envy graph will have multiple sources. Then these triangles indicate the reachability sets of each source. Let's say we have 3 sources. They may overlap, but we make them disjoint, but we make sure that if an agent is in the reachability set of a source, then the entire path from the source to the agent is also in the same reachability set. Okay, so now we do the same thing as before. We pick a G1 and we add it tentatively to the bundle of the first source of S1. We compute a minimally envied subset of G1 union X1, and we let T1 be an agent that envies Z1. Now this agent will not be in the reachability set of S1, otherwise we would be done, but it will be in the reachability set of some other source. So then we take a second good, G2, and we add it to the bundle of the second source. Yeah, G2 XS2. We add it to the bundle of the second source. We compute the Z2, which is a minimally envied subset, and we let 2 be an agent that envies T2, Z2. So this is this, and in general, this will be again in another reachability set. Then we take a G3, we add it to XS3, we compute a minimally envied subset, and we determine an agent that envies it, which will be the T3. Now this cannot go on forever because we cannot have more sources than we have agents. And therefore, after a while, we will construct a cycle. And now we have again a cycle in the envy graph, and we decycle. And if we do this, now we do a cyclic shift of the bundles along the cycle. Along the cycle, everybody is better off, and no strong envy is introduced. And it's obvious what we should return to the pool. Yeah, we remove this G1, G2, G3, and so on from the pool, and we need to give certain things back to the pool. And we can do this as long as we cannot make this trivial move, and as long as the number of goods in the pool is at least the number of agents. So let me summarize. U1 is applicable if some agent envies the pool. U2 is applicable if an unallocated good can be allocated to a source without destroying EF1. And U3 is applicable if U2 is not applicable and the number of goods is at least n. And that means we have shown that we can construct a partition into n plus 1 bundles such that the allocation is EFX and not too many goods are in the pool, and the value of the pool is at most the value of a bundle for any agent. So far for EFX with charity. We have just finished a paper where we improve on this, where we can show that if we slightly relax the notion of EFX, namely 1 minus an approximate EFX, so after slightly scaling down the value of a bundle, the envy goes away, then we can come up with a sublinear number of elements in the pool. So let's see now what happens if n is equal to 2 and we have additive valuations. If n is equal to 3. Well, when the algorithm stops and returns an allocation, there are at most 2 unallocated goods, right? Because the number of the size of the pool is less than n, is at most n minus 1. So if we have 3 agents, the number of elements in the pool is at most 2 at the end. And now we can, how can we allocate the remaining goods? Well, it shouldn't be so difficult to allocate these remaining goods. Well, one of the difficulties is we can show that there is a partial EFX allocation and an unallocated good, such that in every complete EFX allocation, some agent is worse off. Yeah, so you have an allocation into 3 bundles. There is an unallocated good. This allocation is EFX. But if you also want to allocate G, then you have to go to an allocation Y1, Y2, Y3. And at least one of the agents is worse off. So we cannot have these update rules which are monotone. Yeah, all before our update rules were monotone, and this guaranteed termination. Now we must allow update rules that worsen the fate of some agent. And so the termination argument, we also need a more refined termination argument. So our refined argument is we label the agents arbitrarily as ABC, and we look at the value of the first of the bundle for agent A, the value of the bundle for B, the value of the bundle for C. And what we can show is that if there is a partial allocation X and an allocated good G, then we can move to another partial allocation that is lexicographically better. So either the valuation of the agent A improves, or the valuation of the agent A stays the same and the B improves, or A and B stay the same and the C improves. And these update rules are more complicated. So the proof is a 15-page tedious case analysis, and I will not go into it. So then the algorithm is exactly the same, really. We start with an empty allocation, and as long as there's an unallocated good, our invariant is that the allocation is EFX. We apply one of our update rules. The potential function goes up, and this guarantees termination, and then we return dx. And I said it's a tedious 15-page case analysis, and more is true. We have also convinced ourselves that the same approach will not work. So for n equal to 4, additional ideas are needed. I think it's worth I mean, you could say, well, how about n equal to 3, n equal to 4? But it's really the case that in applications, the n tends to be small. The m might be large, but the n tends to be small. Yeah, think of a divorce. The n is 2. Think of dividing inheritance. The n is the number of children. or maybe also relative. So the n in many practical applications, n is not a big number. I close here. I thank you for listening, and if you have any questions, I will try to answer them. Thank you.
Thank you very much. Good. I think just wanted to confirm that your existence proofs are all constructive, right? Because the update
Yeah, they're all constructive. Yeah, they're all polynomial time.
Polynomial time. Okay.
Yeah.
Okay. Any questions to Kurt? There's one.
Come on.
So while we are waiting, maybe can I just take a quick shot?
Sure.
Okay, so in fact, I'm actually stealing a question from Venkatesh. We're just having a discussion in the chat. EF1 and EFX seem like two extreme notions on some spectrum. So in one, you ask for eliminating envy after the removal of the least valued good. And in the other, you ask for eliminating envy after the removal of the most valued good. So is there a natural sliding scale is there a natural in-between notion that's maybe even parameterized by some K where we say, what about eliminating envy after the removal of the kth most valuable good? So in the language of strong Envy-Freeness, where we say that EFX relates to basically envying a proper subset. Now, can we refine that and say, what if you only wanted that you don't envy proper subsets of size at most something? Would that make sense to ask? And if yes, is that being considered?
I've not seen this. What I have seen is that you sort of trade a good. You take it away from the other and you add it to your own. And you ask, you look at xj minus g and xi plus g. And then you compare those two values. And you say, this has been studied. I don't think it's a particularly natural definition, but I think it comes out of the fact that this EFX problem is so hard that people try various variants.
Right, relaxations. Yeah, this was probably also in that spirit. We were wondering if there is something that sort of is a bridge between EF1 and EFX, and maybe somewhere in the middle, it's perhaps as easy to work with as EF1 is, but yeah, okay. So maybe the specific version has not come up in this language, is what you said.
Yes.
Right. Well, thank you very much again. Thanks for that really wonderful talk. I think there are more questions in the Q&A, so I will.
A couple of questions in the Q&A. Can you see them, or you want me to read? I can.
Q&A, yeah.
Venkatesh, there is a question from attendees also. Shall I allow to talk?
Sure. I mean, let's look at the questions in the Q&A first.
What about the envy-free allocation for dynamic indivisible goods? How should we reduce the envy factor? For example, shares. I see. Okay. Dynamic means the value of the goods changes. Whew. I've never seen this. But it's an interesting question. Yeah, I've never seen this. What is the number of valuation functions is small, say 2 or 3, but we don't know who is using which function. So I cannot answer this, but I think I can answer a related question. I was asking myself whether I can search for a counterexample. So remember, we showed it for n equal to 3 and additive valuations. For n equal to 3 and general valuations, it's open. So I was asking myself, can I do a computer search through, let's say, 3 agents and 8 goods, 9 goods, 10 goods, so a small number of goods. And I try all possible valuations. I mean, not all possible, because I mean, the values are real numbers, but all substantially different valuations, yeah, where the order of 2 sets changes. But I didn't find a way to break symmetry. If one doesn't break symmetry in such a computer search, the numbers are just, the number of cases are just too big. Even for, yeah. But this, I would be very interested if somebody finds a good way of searching through all small examples. More questions?
So what do practitioners do if, you know, Envy and EFX is so hard? Do you know?
So what does Splitit do, for example? Splitit does the following. It okay, that's what it used to do 3 years ago. I haven't looked at it, or 2 years ago. So what it did is it computed the allocation which maximizes the Nash social welfare. So what is the Nash social welfare? The Nash social welfare is the product of V1 of X1 times V2 of X2 times V3 of X3. And so it first finds the allocation which maximizes this product. This allocation is also EF1. And Nash has argued that this is an allocation that maximizing Nash social welfare is also a reasonable choice of fairness. And now computing the Nash, maximizing Nash social welfare is a hard problem. It cannot be, it's not in P. So, but they compute an approximation of it. And this is the allocation which they compute.
Can we quantify those approximations? Or is this some heuristics?
It is, okay. How does one enter the valuation function in Splitit? One enters the valuation, it's additive valuations. And the way one enters the valuation is one has, I think, 100 points. And one assigns these 100 points to the items. Yeah, so it's not, so the values of the goods are small integers. And they add to no more than 100. And then one can actually compute maximize the Nash social welfare if the values of the goods are all small integers.
Okay, are there any more questions? Otherwise, thank you very much again.
You're welcome. It's a pleasure.
Great listening to some of your recent results. And now we have a half an hour break, and then we assemble again at 5:30. And Kurt, you are welcome to join for other rest of the talks if you have the time. Otherwise,
I think I enjoyed the sun.
Okay, thank you. Yeah, thanks again for this excellent talk. And hopefully we'll see you in a physical mold next year sometime, yeah, or even sooner. So thank you, everyone.